So let's continue. There is someone who will come. We send invitation. I will accept him. You hear me?
Yes.
Okay.
Yes. Yes.
Okay. Okay. Perfect. So let's continue. We arrived here. So we have to make an adjustment as I took before. Let me see. So we are here. So in any modification, all the changes we may make shall be justified. So do we have the right to make this change or this modification? Based on what we can make this change? So all the changes we make, we will not make them randomly or just like that. So we have to get a justification of our change. Let's see some consideration. For example, if we have in the history match, you have this line of history, it should be data points here, and you have simulation here. So your simulation field pressure is higher than history. So what are the consideration you may see to do that, to adjust this? So the possible modification we can do, we can increase the pore volume. We can go to our aquifer volume, if we have aquifer, and we might change our permeability to make this happen, so that we can have our pressure, simulated pressure, will be equal to our uh, observed pressure in the field. So we may think about some things that help us to get this much of the pressure for this case. Another example, if we have breakthrough time here, so breakthrough time is okay for water cut, for example. After breakthrough, water cut is too high. So in this case, what are the changes we can make? So as you can see at the beginning, we have start, a good start. So, but after a while, after a certain time, so now our simulation is high than our history. So we may try to do something that is acceptable for us. Possible change, we can see, we have to look at the curvature of the relative permeability. Curie component, Curie exponent, for example, we may adjust our aquifer influx. We may see if we have a channeling, and then we have permeability streak, which is not, which is generated by simulation, but in reality it is not. So we may think all the options that we can to have change in order to make our history data points be equal to our simulation trend. Uh, so we always take bring the simulation to the history. Okay. So this is because here, if I told you, this water cut is governed by the skull. You have the relative permeability water is going maybe too fast. So we have to lower it a little bit down to get history history matching. Or you might have your aquifer strength is very high in your model, so we might reduce your aquifer volume. So the permeability is too high because the flow is coming too fast. We can adjust our permeability to reduce this water influx. Another one, this is in the same case, but you can see here, water breakthrough time is too early. After breakthrough, water is okay. So you see here, the trend is the same, but in the simulation got it earlier than what is in the field. So it is another problem than the first one. So this one, we are okay at the beginning, but we have the deviation. Yeah, simulation is higher. But at the time, T, you see, we have a good start. But in here, you have we are in our history, for example, here 2010, here 2005. So in the model, we have early breakthrough, but in the reality, we don't have. So the trend is okay. So we may think about things that may make this change to get to make a shift of the simulation towards the history. So what are the possible change? So we may change the endpoint simulation, relative permeability. In this case, mainly it is the critical water saturation. Permeability of well to aquifer. So we may see how is the permeability of the aquifer. So in this case, in your simulation, when you have a high permeability of the aquifer, so the water is coming faster. So we have to investigate this case. Shade between wells and aquifer also, maybe there is shade or something. So we have to review all this in order to get our simulation going towards our history. So in simulation, it is always like this in general. So we have some discrepancies. Our simulation trend is not matching to our history. So we have to find a way how to adjust it. And then we have to make our justification how to do so. Sorry. So we have to, in initially, when we run our simulation, we have to confirm our volumetrics, because this is very essential. We should have consistency on the hydrocarbon in place. So volumetric calculation between coarse grid or upscaled model and the fine grid original. It depends which model we are using in our simulation. But mainly the upscaled and the original and fine grid should be very close. Let's say we are accepting 5% error when we calculate the from volumetrics method. So when we see our simulation, we have to be very close to these numbers, geological volumetric numbers. And then if we are not very close, we have to seek we have to be in agreement. We have to make the changes to be very good. So visualization of the static model reservoir property verify the consistency, the gaps, the mismatch, check well trajectories. So when you got, for example, a geological model from the geologist, you have to check all what, for example, well trajectories. You will see them in the model. Maybe there is the discrepancies. There is some gaps. There is some faults not well done, and so on. So we have to visualize the static model before we start our simulation and see what is in there for to make a good start. And if there is something abnormal, so we have to go back to our geomodeler and tell him this is not acceptable, or there is, you have to make modification. He will do it for you, and then come back again to you with new revised model, and then you can work on it. So we have to adjust the scale data if simulated parameters are higher or lower than observed. This is generally happen. We adjust permeability to match rates and pressure. It's a global permeability or local permeability of a given area. We have to change to match. We may change also porosity, pore pressure, pore volume, if necessary, to adjust the volume. So this is the consideration we take for history matching. What are the things that we have to match? So compulsory, like we have to match them, general. So we have to match bottom hole static pressure, production water cut gas oil ratio, breakthrough time, if we can, bottom hole flowing pressure, tubing head pressure. Mainly, all these parameters should be matched. Like I said, matched, we also fair matching or good match. We are going always to the best match. So sometimes it is necessary to average the production such as oil rate, water cut, and GOR. The time interval for averaging the production data should be determined by simulation process. The harder the process, simulation time step is required. Conning study frequently show of the wells. So we have to consider this time interval for time steps in order to get the match by adjusting the time steps items. In general, logarithmic scale should be applied. Start small, then become bigger at simulation front proceeds. Try to design the time steps, then honor significant field events such as through breakthrough, pressure measurement, stimulation, and open. This is just how we adjust the time steps in order to get match. So the next important parameter to be matched may be water cut and GOR. I already talked. Saturation logs, we have to, if available, we have to match them in the model. Mainly saturation, water saturation log. Also useful to be matched. All other data are normally treated as supplementary So vertical flow performance tables are required if one tries to match tubing head pressure. So this vertical flow performance tables, these tables will take into account the pressure loss in the tubing. So if we want to match the tubing head pressures, we should have these tables to take into account this pressure loss, and then we can match our wellhead pressures. Generally, we don't do this in the history much, but these curves, these tables are required in the forecast. In the forecast, to calculate what is the our tubing head pressures. Oil production rate is usually measured systematically and accurately. But if we can measure the WR and GR, we are not measuring. But we assume that they are okay because it is just ratios of what we are measuring. Injection data can be less accurate than production data. Yeah, this may happen because of the injection module. We may have not very well flow meters to measure these injection rates. We may have some consideration to take into account to have good accurate data. That's why we said at the beginning we have to quality check all the data that we put inside our simulation model. So if it is well checked, so then we have justification to do our change, our modification. So in order to get this validated data matched with our simulated data. So we also have uncertainties. Generally, whatever we do, we try to do our best to make very good model, static model and dynamic model. We are always doing our best, but always we have uncertainty. So we have high uncertainties and low uncertainties. For high uncertainties, we can say that pore volumes, permeability, transmissibility, KV sur H ratio, relative permeabilities, aquifer properties, oil saturation, mobile, fault location, and their properties. So all this we are something we are generating from the model. So and something are we are measuring them. For example, the KV sur KH ratio, we cannot measure this one. So in general, it is assumed. We assume that generally KV is equal 0.1 kz. For example, the horizontal permeability is 0.1 of the horizontal permeability. But there is no measurement. And then, as you know, inside the reservoir, we may have a very long change in the facies, in the characteristics, and so on. But we have to do this assumption. Transmissibility, we cannot check. For example, aquifer properties, rarely we have wells crossing the aquifer and taking cores and making loggings and so In the aquifer, also we have generally doing assumptions because we have a lake of data for us. The fault locations, for example, the faults, if we don't have, for example, well testing, you have to do, for example, a long build up to reach the boundaries, and you may find that your fault it has given distance, your well is at given distance from this fault. And then you may say that my fault is okay. There is a fault at that distance, and this fault mainly it is not found by geologic, by seismic, but from because the faulting there is a resolution how to get it. For example, if there is through of less than 30 meters, we cannot detect the fault. So by well testing, you can. And therefore, you have to do long well test to see these faults. And then you will know what is the distance to that fault. Then you may go back to your geologist and said, oh, from well test we got this. So is it in your model? Let's check. And then you will have discussion on this and on all other properties. And all this to in order to make better history match. Low uncertainties also, we may have some low uncertainties from the measurement. So we may have fluid properties are usually considered uniform through the reservoir. This may also change a little bit, but generally, if our sampling is okay, so we have to rely on what we have and we consider that is valid. So we may say that fluid properties are at low uncertainty. So if you have thick reservoir, fluid might be great with depth. So if there is a change in depth, so but anyway, if we have to consider what is available in our, so the rock compressibility might be at low uncertainty, capillary pressure, datum, initial fluid contacts. So initial fluid contacts, you know, we determine this initial fluid contacts by petrophysical from the logs. So we have to consider that our contacts we define it are accurate. So we may have some meters of difference, but datum pressure is not. Normally, we have to set this datum pressure, so there is no problem for this. So generally, this is the low uncertainties. As I said before, the high uncertainties, and here low uncertainties. So we have some steps to succeed our history image. Set the problem and define the objectives to understand the reservoir characteristic, fluid dynamics behavior with the clear objectives. Make it simple. So don't complicate a lot of things. Make it simple. As we said, keep it simple. Start and end with the simplest model, which is consistence. So we'll be back again. Huh? So model is consistent with the nature of the reservoir. Objective study and work with the reasonable consistency data. Try to understand your model limitation and capabilities. Understand connected system. So reservoir are connected through wells from bottom hole to surface facility via tubular tubing or pipelines. So often the isolation of different compartments of the system for separate study may lead to an inappropriate results because of the neglect of interaction between different parts of the system. So the system should be good from reservoir to surface. However, when appropriate, don't be afraid to break a big problem into smaller components. This can lead to not only substantial saving, but greater understanding of the mechanisms involved. Before starting full field study match, define and rank data that need to be matched and their tolerance, which might be depend on. So objective of the study, data quality, model coherence, time and budget available. So when we do history match, we will not spend years on it. So because there is time and there is budget for it. So we have to go to our objective directly. We have to quality check our data, our model, and then working to get best match. So as procedures, we match the pressure first. So utilize all information from course grid versus aquifer, volume, and overall permeability distribution. Set the model to be at voidage control. If you can control, because in simulation we are always making controls, control by volume, by rates, by pressure. We adjust aquifer properties, total mobility, and transmissibility if we can. So here we just say that we have to match the pressure at first time. Second, we have to match the rates. So try to match the highest level first before trying each individual ways. So we have to match the volumes or the rates, for example, of the field, then the groups, then the reservoir, then platforms, or depending on the degree of that. So we start by the field and the reservoir, and then if we have groups, and then if we have platforms, and so on. So we can adjust for that relative permeabilities. Mainly the skull, we have to adjust it. We have to make sure that these rates are well reproduced. So to get a good history match, I mean, for good predictions, so we have to see our rates well matched with our observed data. We can match our PI, well PI. If we have the PI, and then we have to set the value of the PI we obtain it from other source. So if we have well test, you do your PI correctly, and then you can set value to match it. Check the well deviation data and perforation data. We have to assume a cache allocated may be incorrect. Modify skin cache PI to match the following bottom hole pressure. So we have to to make modification based on the our understanding of the reservoir and our results from other sources that we have. For example, the PI, you can do work and determine your PI, your KH, your scheme from well test, for example. So for this, you make changes to match your parameters. So the match of pressure of average is affected by fluid volume in place, size of the aquifer, degree of communication between reservoir and aquifer. So this is the pressure. I mean, the pressure is supported by this pore volume, aquifer size, communication between reservoir. That's why I said before we may go to change pore volumes to match the pressure. We may go to our aquifer size, aquifer volume, and then, but we may change our transmissibility between the reservoir and the aquifer. So pressure drawdown is affected mostly by horizontal permeability and by skin effect. We also have, may have, because we know when you produce, you have this permeability. When we have the drawdown in the one region, horizontal wells, we may have conings and water production. So I may say that the pressure is affected by high drawdown. Matching breakthrough time is difficult, but breakthrough is sensitive to traction errors, numerical dispersion, which is normally required to fine grain for the model. So there are some things that it is not easy to match like breakthrough time. So workover and GUR depends primarily on drawdown. Again, the permeability, but also on the position of the fluid contacts. Fluid contacts, if we are very close to the fluid contacts, so if we produce a very high drawdown, we may have water coming early. So we have to take in consideration the well position, or our well is in the transition zone. So we have to look at our PCs. So the shape of the curves after breakthrough depends on the relative permeability curve, depends on the point. So fear these problems of the GUR and the water cut related to water oil rate and gas rates, we generally go to make change in our scale data. So just here example, full field history match of cumulative oil and water production. We can see here we are matching observed oil and modeled oil. So the dots, you can see the dots are on the superposition on the simulated. So here is cumulative production of oil. This is water, cumulative water. So in this field, we are matching perfectly. So in this field, like here, the water is reproduced at the same time as the simulated. So this is a perfect match, but we can say that is a perfect match. So this is cumulative, but cumulative is depending on the